Okay, good morning. So today we're going to see neural nets from a practitioner's point of view. Okay, so last week on Thursday was the last heavy part of the course on the theory of things. So from now on, it will be more about the practitioner's point of view. Okay, so just to summarize what we've done last week, so it's kind of a bit fresher in your mind, okay? So last week we saw that we could organize operations, any kind of operations, into a graph of operations, okay? So that's really kind of parallel with programming languages where you have functions and you have inputs, and you're just trying to compute something by combining these functions. So we thought that so this is the analogy with a neuron, okay, remember? So we said that artificial neuron is loosely based on an actual neuron because there's these two parts. The first part is the linear combination of your inputs. So you combine, you do a kind of a summation of all the signals for your input, and then you pass that through some kind of nonlinear function, okay? And we saw that there's different types of nonlinear functions. So here are a few of the most popular ones. It's important to realize that there's these two parts in a neuron, the linear part and the nonlinear part. The linear part, if you want, is here to go from, you have n inputs, and you want to combine this n input into one single number, okay? So the linear part of the neuron, its job is somehow to do a dimensional reduction. So we start from a n-dimensional space, the space of all your inputs, and somehow we need to aggregate all that into one single number. And to do that, we're going to use the linear transformation. And then we need to apply some nonlinearity, and that's the job of the activation function. If you don't have any activation function, if everything is linear, then you can't go very far, okay? So you're combining all these functions would just lead to more linear systems, and you don't get anything from that. So you need both aspects. You need to reduce the dimension of your space to get to one single number, and then you need to apply a nonlinearity. So we saw that you could combine all these neurons or units into these graphs, and these are called neural networks. One point I made quite early on was that although neurons are a good idea, okay, having all these units as being neurons is a very good idea because you can actually approximate anything. It's good to remember that these don't have to be neuron type units, okay? So you can apply any function, you can, only these intermediate units can be any kind of function you want, okay? Right, so we saw that there's the theorem that tells us that you can approximate as good as you want any functions into neural nets. So that's a good start. So we have now kind of a framework to say we can do machine learning the way we want, and we always will find a network that will just work out fine for us. Then the question was, how do we optimize for this, for the weights, for the hyperparameter of your model, and for the parameters, sorry. And then we looked at something called, so we realized that, sorry, going there, we realized we could use the gradient descent, okay? So this is what we've seen with logistic regression. The idea is that you update your weights by computing the gradient of your loss function. And really what is happening here is like, you imagine your loss function as being a surface, okay, it's called a manifold, and you're trying to go down the steepest slope possible to go down to the minimum of that function. And the steepest slope is given by negative minus the gradients, okay? So the idea is like, think you're in a mountain, you want to go down to the deepest point of your valley. What you do locally is you look at the direction of the steepest slope and you go down that way, okay? So this is the algorithm. It's a very generic purpose, works with any kind of function, and it's all fine, but we need to compute the gradients. And computing the gradient is non-trivial. We saw that we use one algorithm called the backpropagation to do that. Okay, so I'm not going to go back to the backpropagation, but basically it's the most efficient algorithm we have to compute the gradients. So we have pretty much everything. We have the model, so the framework of the neural nets, and we have a way of training our system to learn what the weights are. A side note here, this is just one optimization among others, okay? It turns out that's the most efficient one to date. Maybe in 5 years' time, 10 years' time, what we learn is that you don't need to use gradient descent, and you can use different optimization strategies, okay? So keep in mind that all the constraints we have right now, and I will talk about computing the gradient and so on, the backpropagation, is just one practical consideration, okay? It's just one of the solutions we have. It just turned out that's the best one we have right now, okay? Okay, so this is the idea of the backpropagation. You propagate backwards the evaluation of the gradients. Right, so today I'm going to look at a number of issues and points from, I say, from a practitioner's point of view. So what is important with neural networks is the architecture, okay? So this word you're going to hear quite a lot. You know, how do you architect your network is kind of the main consideration. And we know from experience that going deeper, so having more layers, is good for your networks, okay? So the deeper you go, usually the more expressive your network is, and the more interesting the features you have. So as a rule of thumb, you want to go deeper. The problem with going deeper is that it's harder to train. And so this first point we want to make here is called the problem of the vanishing gradients. So what you see here is some kind of a toy deep neural network, okay? Now it's very deep because you have actually 1, 2, 3, 4, 5, 6 hidden layers here, okay? Now each of the layers just contains one neuron, okay? So one unit. So it's quite that's why I say it's a toy example. In real life, you will have way more neurons per layer, but it's just to give you an idea of what's going on. So this is your input, x. This is the parameter you're interested. So the first function is a function of your input and a parameter. And then you're going to apply a whole bunch of different functions to this, this first unit. Now remember, when we're thinking of layers, is to say each layer transforms the previous layer into a new set of features, okay? So if you think of the result of a particular layer as a set of your feature, then when you go to the next layer, you basically retransform your features into a new set of features, okay? So here, we set it from a feature x, and we transform into a feature u1 of x, and then to a feature u2 of u1 of x, and so on, okay? So we retransform the same feature 6 times in this case. Okay, so we know we need to compute the gradient of the loss function with respect to the parameter w to do the gradient descent. And the backpropagation algorithm here is quite simple because the chain rule actually has a very nice form in this case. And you can see that the gradient of E with respect to the loss function with respect to w is simply this product of all the steps to go from the loss function to u6 to u5, and so on and so forth, okay? So you just have the product of all these terms. Now here's a problem, okay? It's a product. So what happens is that if any of the intermediate derivative is 0 or near 0, then the product of all these numbers is going to be 0 or near 0, okay? So if it just happened that, say, d3 over d2 is very close to 0, then dE over dW will be very close to 0, okay? So it's a product of numbers. If one of the numbers is small, then the whole lot will be quite small, okay? And this is quite a problem because here's some examples of, so first, let's see how frequent this might be, okay? Is that really a problem, how frequently that will happen? So here's a few examples of the derivative for some of the popular activation functions you have for your units, okay? So if you look at the sigmoid, this is the derivative of the sigmoid. So this is mostly 0, so if you go further to the left or to the right, that would be mostly zeros. And it's only non-zero in the central parts, in a very narrow range of values. Same for tangent h, and the ReLU is the rectified linear unit. It's a bit better, but basically it's 0, exactly 0 for all the range from -infinity to 0. Okay? So what you can see here is like for all the activation functions, okay? So remember the activation functions in our case would be our u's here, okay? So for most of these functions, when you look at the derivative to these terms, okay, then you realize that there's a massive range of values for which this derivative is 0, okay? So if it just happens in your training that at some point your values are close to one of these, this range, if you fall into that range for any of these values, then you're going to be 0. And the problem is that range is actually the most of your available range of values, okay? So chances are you will fall into, at some point into that trap, okay? So one of the values is going to end up being 0, and then the resulting gradient is 0. And because in the gradient descent algorithm, you use that value to move forward, that's your step. If that step is 0, then you're stuck, okay? You can't move forward anymore. So if you hit a region where it's kind of like a plateau, if you want, okay? So if you hit a plateau where everything is flat, and you ask the questions, go to the steepest descent, you'll be like, well, I'm stuck because there's no such a thing as a steepest descent. Everything is just flat, okay? But this is kind of the problem you have, okay? And sadly enough, there is no correct answer to that question, okay? So it's kind of the biggest weaknesses of neural nets, and it's one of the biggest challenges is how to deal with vanishing gradients. Now, I come back to that, okay? Here it really stems from the fact you're going deep, okay? I simplified the network, but this product comes from the number of links you have from your weights to the last function, okay, to the last node of your graph. So if you think of recent networks, they have, 50 layers, okay? You would have a product of 50 numbers at this point, okay? And you have to somehow hope that none of these 50 numbers is going to be 0. Of course, in real life, in real networks, the situation is slightly more complex because you don't have just a sequential network like that. You have different neurons and they're all connected to each other, and you have, if you remember, in this kind of configuration, a unit is connected to different other units, okay, from each layer. When you go from one layer to the other layer, you're connected to all the other units, and remember you have these sums appearing, okay? So you sum over all the possible passes. But still, it is an issue, okay? Even so, there are aspects, practical aspects that make this problem a bit less intense. It is still an issue, and practically what it means is that it's very easy to train. When you do the training, you train this last layer very quickly, okay? So when you have an input, so you have your observation, you have what the output should be, and you compute the error function, and then you can backpropagate the updates, if you want, on the first layer, okay, on the last layer, okay? And that backpropagation doesn't suffer from this product, okay? It's just you apply straight the differentiation. So you can update this layer very well. This layer, not so well, because really you have to go through that update of the last layer. Okay, so you really have one intermediate results. And as you go further down, up to the first layer, then you have all these products that start to emerge. Okay, and that means that if it's easy to train the last layer, it's very hard to train the first layer. Okay, so the information it's very hard for the information to go back all the way down to the first layer. Okay, so kind of a diffusion, if you want, of information going through your network. Okay, so that will be something interesting. You will see, especially with convolutional neural nets and so on. You will see that it's quite an issue to really get the first layers to look the way you want them to look. And it will take awful lot of iterations. Okay, so that's the quite important aspect. Just to say, even so it's an open problem, there are a number of strategies you can do, and there's been a number of recent architecture that allow you to go quite deep. So something we'll see next week, it's ResNets, and it's called residual network, and they have a mechanism in place that allows you to jump from layer to layer so as to propagate the gradients all the way down to the first layer. And that allows you to go from, say, what was the limit, around 17 layers to 50 layers. Okay, so at some point we were stuck at 17 layers around that point, and then this architecture we are able to go to all the way to 50 layers. Anyway, something to keep in mind for later on. All right, so let's look at some practical consideration. Okay, so the first thing I want to say is that it's a gradient descent algorithm. Okay, so you're not guaranteed to find a global minimum. Okay, so you've seen some of the examples. I don't know if you played with the TensorFlow playground. You'll see that sometimes it just doesn't work. Okay, and so there's a number of things you can do to go around that. Okay, there's a number of optimization tricks you can play with, and basically, as a practitioner, you're going to end up trying all sorts of things until it works. Okay. And there's no nice way of going around that. It's just trial and error, and you just, that will be your bread and butter for quite a while. Right, so the first practical point, okay? So remember gradient descent. All the networks I've drawn were for a particular observation, okay? And the idea was, for most loss functions, in fact, it's just an average of all the particular loss function for one observation. Okay, so if you have a data set of 1 million observations, the overall loss function, either the sum or the average of the particular loss function for each of these observations. Okay, and so in theory, if you want to compute the gradient for the entire loss function, you need to evaluate the gradient for every single particular of these observations. Okay, so for every single new observation coming in, you need to compute the backpropagation, evaluate where the gradient is for that observation, and then average that for all the values of your data set. Now, obviously, it's a bit of a problem because you know that, first, your database could be very big. Okay, you could have, as you know, billions of data, and if you need to go through the entire data set to be able to compute the gradient overall, it's quite costly, okay? Plus, you know that you will need to iterate multiple times because your gradient, you probably need a few 1,000 iterations or 100 iterations of your gradient overall, okay? So it's probably not very practical, and so the way around that is to use what's called mini-batch gradient descent, okay? So what you do here is you say, I'm going to split my data and partition it into different batches, say size 16. Okay, so you take groups of 16 observations at a time. So instead of computing the average gradient for all the observations, I'm just going to take 16 observations, compute the gradients using backpropagation for the 16 observations, And I'm going to average the gradient for the 16s and use that as an update for my weights. Okay? It's more practical. Okay? You only need to do 16 backpropagations before you get an update for the weights, and then you can move on. Okay? The size of your mini batch. Okay? It's quite an important parameter you have to play with, but usually trying to keep it quite small. Okay, you don't want to take hundreds of thousands of your samples. You just take a few of your samples. The extreme case, the mini batch is of size 1. Okay, so what that means is that every time you have an observations coming in, you compute the gradient for it. And then you just say the gradient for it is probably the same as the gradient for the entire loss function. Now that's totally wrong, of course, but still, you go for that. And you update your weights accordingly. Okay, so every time you have new observations, you look at the update given for these observations, and you just update your model. Now this is called stochastic gradient descent, and if you don't like the fact like it's wrong, it's actually in a way a good thing, okay? Because coming back to the problem of the vanishing gradients, sometimes you get stuck, okay? So the gradient is null, so you still want to move somewhere, okay? So if you average your gradient over a huge range of data, maybe your gradient is going to be near 0 as well, okay? Very, very weak. But if you allow your gradient to be changed, computed from observation to observations, then you're going to have some kind of a bit of a noisy update, okay? So your gradient will be a bit random just because, of the way you picked up your sample. And therefore, by taking these random values for your gradients, you will be able to get out from your flat region, okay? You're going to artificially say, I'm going to move in that direction, even so it looks like it's flat, okay? So, say that again. Mini batch, you split your data set into little batches of observations. You compute the gradients at the average of the gradient for these observations, and you can reduce that data set, the mini batch size to 1, and that's called the stochastic gradient descent, and that allows you to have some kind of a bit random gradient descent algorithm, okay? And the fact it's random is not necessarily a bad thing, okay? But it's to be checked. So, as always in these kind of situations, you try different mini batch sizes. Maybe for your problem, you don't want that. Maybe for your problem, you need to have a larger batch size. Maybe you need 32 values. Maybe you need 8. Maybe you need 4. Okay, and it's really you kind of it's a bit about luck. Okay, so how lucky are you going to be about your optimization? All right, so you need to try the things. All right, so a bit of terminology. So an epoch is the number of times okay, so if you say you've done your training over 2 epochs, okay, so it's how we're going to measure things. We're going to use the number of epochs. And an epoch means that you've seen all your data at least once. Okay, so let's say you have a data set of 100 observations, and let's say that your mini batch size is 10. You will do 10 updates of your gradients per epoch. Okay, so your epoch, so here n is 100, and your batch size is 10. So 100 divided by 10, you'll have done 10 updates of your gradient. So you'll have computed your gradient 10 times in one epoch. Okay, so one epoch is you've You used all your samples once, okay? If you do a batch size of the entire data set, then you will have done only one update of your gradients in one epoch, okay? Because you will have 100 observations. You use 100 observations for doing one update, so therefore you've already completed your update with just one epoch. All right? We use epochs. It's kind of a way of, it's your constant cost, if you want. Okay, so if you just measure in terms of progress of your loss function in terms of the number of iterations, it's a bit misleading because if you increase your batch size, then obviously it's harder to compute. It takes more time to compute the gradients. Whereas you have a fixed cost to progress through one epoch. Okay, so one epoch is a constant cost, if you want. One small detail here: once you finish an epoch, usually you reshuffle your data, and that's to avoid repetitions in your pattern. Okay, you don't want your mini batch size, you don't want your mini batches to always contain exactly the same samples. Okay, so you want to shuffle things around so you don't get periodic patterns and so on. Okay, so that's for a bit of technology. So you've seen epoch, you've seen batch size, and because at the heart of neural nets, the training you have, the gradient descent, as you probably will know, what we've seen is just kind of the vanilla gradient descent, and there's a lot more techniques that you can use for that, okay? And they're all based around the same principle, but they're slightly different. So what you see here is, so the blue lines here is the ISO contours of your loss function, okay? So it's kind of elevation maps, and you can looking at the levels in these elevation maps. And what we want to go to is this part of the function. This is where the minimum is. Okay, that's your valley, and you want to go down there. But in your process, you start here, and the gradient descent tells you to go all the way here, and then you come back, and you come back, and you come back, and you come back. And you've seen that for when we talked about logistic regression. The same consideration here. The problem is it's easy to overshoot, okay? Now, you can fix some of that by tweaking your learning rates. You say, okay, maybe the learning rate here is a bit too strong, okay? So we're kind of overshooting, so maybe we should go down a notch. But the real issue here is like it's a shape, it's a topology of your valley, okay? If you have a valley that is very deep and very narrow, but very kind of flat at the bottom, it's always going to be hard for any gradient descent to reach the minimum. So there's whole sorts of techniques to go around that. I'm just going to briefly outline some of the ideas behind some of the other techniques. Okay. So the idea here is like if you look at the history of what's going on in your algorithm, okay, you will have something like that. Okay, so if you start to observe that you oscillate, you could try to be smarter about it. Okay, you could try to say at these points, for instance, okay, you could say, well, I know that I've been going down this way. It's kind of a bit curious that I have to go back all the other way right now, okay? So instead of going all the other way here, maybe I should dampen, if you want, reduce that decision, okay? So that's a gradient, okay? The gradient tells me, go this way. But I know that just before I came back this way, okay? So most likely, I'm in a scenario where I oscillate. So maybe you shouldn't go all the way there. Maybe you should go, refrain yourself from going all the way in the steepest direction. Okay? So you just dampen a bit here. Okay? And the way you do that, okay, there's different ways you can do that, but basically you can have temporal analysis of what happened in the past, and trying to predict and say, okay, I know that my gradient here is a bit incorrect. Maybe I should, limit the range of the variations and so on. So different strategies are available, and they're all implemented in any of the toolkits you will have. Okay, so one of those is called the momentum update. Okay, so the idea is a bit what we showed before. Like you want to see what the momentum is. Now the momentum is, if you want, it's kind of it's kind of a filter you apply on your updates. Okay, so this is how it looks like. So this is the update on your weights. Okay, and you see that you update not directly by the gradients, but by this little vector v, and the vector v is what it looks like. So it's given by the update as in gradient descent. Okay, so that's your steepest direction. But as well, you mix it with what was the previous a portion of the previous vector v. Okay. So basically, you kind of have some kind of inertia in your updates. You say, if my update is in one direction at a particular step, I want to go into that direction in the next step as well. Okay? So you say, I want to go 90% in that direction, basically. But you will allow for a small change by looking at the gradients. Okay? But if you're on the default attitude, it's like, if I went one direction in the previous step, probably I should go into that direction again, and only going to update by a tiny bit the direction that is given by my gradients. Okay? So the idea is like, you don't just trust 100% the gradient information, you're trying to integrate this information in time. Okay? You're trying to average out this information in time and trying to see for trends in the direction of the gradients. Okay, so this is the simplest technique here for the update you can have. There's a lot more to it. I'm not going to go through all of those. Just know they exist, and I'll put the names for them. And I'd say the most powerful I've seen from literature from my PhD students is if you have a choice, just go for Nadam. Okay, it's the name of one of those, or for Adam. Okay. But obviously, once again, okay, it really depends on your particular problem. It's well possible that maybe the vanilla version actually is the best for your problem. Okay, it just happens your data is structured in a way that it's better. Okay, so this is one of the. So I put a link here to the Stanford course where you have more detail on all these techniques. But the main thing here, I want you to know that these techniques exist and they need to be tried. It's good practice for you to try different techniques. But when you start, I advise you to start with Adam or Nadam. Okay? Right, so let's go to something you will have to do in this lab this week. It's about regularizers and constraints. So remember the problem we have, as in any kind of machine learning problem, is data. Okay, we want to have loads of data to be able to fit things. Okay, so remember the course on least squares. We want more data, and remember what happens. Like sometimes you don't have enough data. So a cheap way of going around that is to introduce constraints or penalties, and they're called regularizers, okay? There's two types of regularizers you should know about, is the L2 and the L1 regularizers, and this is kind of similar to the talks we had before. So if you look at the L2 regularizers, all what we're doing here is we're saying, if we want to add a L2 regularization term for a particular weight, so I'm just taking Wi as a particular weight, the effect of it is basically we're going to add to the loss function a little term in lambda Wi squared, okay? We just add a penalty for Wi for being different from 0. Now this is like our Tikhonov regularization in this square, okay? So we just say, all things considered, I don't want my Wi's to go bananas. I don't want them to be super large. I want them to be, if I have a choice, to be small and compact and close to 0, okay? So this is probably the most common one, the easiest one, and, to have. You have the least amount of problem with it, I suppose. And one regularization, you have a similar type of idea. So you penalize deviation from 0, but this time, instead of a squared error, you add an absolute error. Okay, so you take the absolute value of the weight itself and add that as a penalty. L1 regularization, no, I won't go too much in detail why, but it has an interesting property, and it's used a lot in what's called sparsity. Okay, the effect of adding L1 regularization is that if your lambda here, like if the penalty is strong enough, then basically in the optimization, it will turn out that some of the weights, some of the Wi's will actually be set to 0. Not to a value close to 0, but actually 0. And that's interesting because you might think, okay, you could start from quite a dense graph with a lot of connections everywhere, and you have a lot of terms, and but you know that your problem is probably a bit smaller. By putting an L1 regularization, what could happen that some of the weights will be set to 0. So effectively, some of your nodes, okay, so from your neurons, will be switched off. And in a way, you're going to obtain, like after training, you will see that by just looking at the one that is 0, you will have a simpler graph, okay, with less connections, less neurons, and which is kind of an interesting concept. You start from a blank canvas with loads of neurons, and then you end up, after training, with a network with fewer neurons, a kind of a more efficient network. You don't get that with L2. In fact, L2 prohibits that somehow, okay? So the weights will get very small, but never 0. In fact, they don't want to become 0. In practice, just go with whatever is simplest. Probably L2 gives you easier conversions, okay? So it's probably easier to manage conversions with L2. L1 is a bit trickier when it comes to convergence, okay? Anyway, so I put a link here to the Keras documentation. If you look at the Keras documentation in detail, something that I really advise you to do, and you will have to do, you will see most of these concepts as part of the API. Okay, so most of the techniques the terms we talked about will be present in the Keras API. Last type of constraints or regularization I want to talk about is an explicit constraints. Okay, so these are kind of soft constraints, if you want. Don't really stop the numbers from being a value. I just penalize them. And here it's a hard threshold. Okay, the idea is like you make sure that the weights are always within some range. Okay, so if you see a weight value that goes higher than some number, you just say, right, it's not possible. Stop it, clamp it there. Okay, so probably not as useful. Okay, let's say penalty L2 or L1 is probably better, but the idea here is like you constrain, and it's kind of for the vanishing gradients and all this kind of stuff as well. They will have an effect. You just say I really, at no cost, I want the weights to be too large. Okay? But it's the same idea, okay? So you have constraints, you have a prior information on what the W's should look like. The last one point is, sorry, where is this? Oh, that has disappeared. Okay, the last point, controlling your algorithm. So we set up the mini batch. We looked at regularizers. And one thing you can think of doing, and you've seen me doing that in the TensorFlow playground, is you can change the learning rate as you go along. Okay? So typically, you start the learning rate quite high, and then what you want to do is called annealing, which you just want to slightly cool down the value of your learning rates. Okay? So by cooling down, I mean you reduce the value or you decay the value of the learning rate as you go along. So you have different formulas. You can have exponential decrease, or you can have different ways of decreasing your value of the learning rate. But the general idea is like you start at a high value of the learning rate, so you try to go fast to interesting region of your space. And then when things start to get a bit subtle, you just want to reduce the learning rate, and at the end of your training, you use very small values of learning rate to really fine-tune your details. Okay? So another strategy available to you. Okay, and the last one, and that is still related to convergence and regularization, is dropout and noise. Okay, so sorry. So remember what I said. Okay, when you have overfitting, which you want, okay, you want to overfit. That should be your first aim. You should, design a network. You want to overfit it. That's the first thing. If you're not overfitting, it's not good. Okay, you want first to overfit your training set. But thereafter, you want to, to do the right thing. You want to reduce the overfit. And we know that overfitting, one of the issues is we don't have enough training data. Okay, so in theory, you wouldn't have overfitting if you had an infinite amount of data, but you don't. Okay, so one way of going around that is called data augmentation, and the idea is the following: you're going to generate some small variations of your data sets. Okay, so you have, say, a limited amount of data observations, but you can jitter these observations in some ways. Okay, so one simple way of creating more data from the limited amount of data you have is to add noise to the features. Okay, so you record, say, images. Okay, you have a lot of images, and what you could do is you just add a bit of noise to your images. Okay, so you just take your input image and just generate 10 versions of that image, but with slight little differences because you added noise, or you could change the brightness, the contrast. You can do, you can shift the picture a bit, you can rotate a bit the picture, you can create small versions of that picture. Okay, so the idea is like you have your data set, you're limited, but you can quite easily, in most cases, come about like generating more data from what you have at not too much cost. And so one technique that you'll find in Keras and so on is you can just actually add Gaussian noise. They will tell you, okay, you can add some noise to your data, to your features. Interestingly, remember that neural nets is a way of transforming your features into more complex features. Okay, so if you think about it, if you add noise to the original features, why not adding noise to the transformed features? Okay, so the idea here is like you're going to add noise, but not only to the original features, but to all the intermediate layers you have. Okay, so you're going to add some kind of noise on these transformed features, and that means that this noise will be more structured in a way. Okay, so if you look at, you will produce. Let's come back one step. Okay, So remember here, we are at hidden layer, input layer. We can add some noise, and that noise on your features that augment the number of data we have at that layer. But we can do the same process. We can say, well, we're going to learn really the hidden layer 2 based on the hidden layer 1. So we could say, if we produce hidden layer 1 as a transformation of the input layers, at that point, it's almost a new problem. And so what we could do is we could do the same trick and say we could augment the data by adding noise to the result of hidden layer 1. Okay? And in doing so, you just generate more data for yourself. Okay? But this time, you create versions of the data that's kind of more interesting. So say, the analogy for images would be, you could take the pixels, add Gaussian noise, and it would be something very noisy on the pixel level. But the next step would be, for instance, you look at the DCT. So you look at the JPEG compression. So you apply JPEG compression, and you start to do noise on the coefficients from your JPEG. And now what you have is a distortion at the JPEG level. Okay? So you have different type of distortion, different type of noise applied to your pictures. And that will help you make your system more robust to any kind of JPEG image now. Okay? So that's kind of an interesting way of generating more interesting noise and making your system more robust. So this happens during training. So every time, obviously, you stop the noise for the evaluation. Okay, you only use this noise. You only add this noise while you train. Okay, and once you finish training, you don't want to add noise, obviously. The last example of that is called dropouts. Okay, and it's quite it's the same idea. Okay, but this time instead of adding some noise, we're going to multiply the outputs, the units by the noise. And the multiplication, it's just 1 or 0, okay? So the effect of that means that you are going to randomly, at training time, switch off or switch on some of the units. We're just going to say, instead of having the output of the units, whatever it is, okay, and we use that in the computation of the back propagation, here we're going to say that the units, the output is 0. Okay, we're going to randomly select a number of the units and say, for that particular gradient, the way we're going to compute it, we're going to set all these units to 0. Okay, but the same idea here as in adding noise. Okay, it's just a different kind of noise, right? But it's a very simple process. Okay, so you train your data, you have new samples coming in. You want to compute the gradient for these samples. And but what you do is you're going to switch off some of the neurons at random, and you're going to see what happens, and then train the network according to that. Obviously, when you evaluate the network, you reuse all the neurons you have, okay, all the units you have. Okay, I'm just going to fly through the last points. Main thing to do is, because training is tricky, and that's the main thing you have to look at, is you need to graph everything you do, okay? So you need to monitor the loss functions you have. Now, we've seen a bit of that already. Now, in the axis, I don't put the number of iterations, I put the number of epochs, okay, for the reasons I discussed. But you can learn a lot from what's going on in your neuron and your network by looking at these graphs. So in this one, so you have the loss against the epochs, and that's a graph you'll have to plot, to see what's going on. And here, what's going on is you can detect whether your learning rate is correct or not. Okay, so if you're going up like this, it means your learning rate is way too high. There's something wrong going on. Obviously, you want your loss function to go down, smoothly and nicely, and all the way to very low level. Okay, if you cannot reach a level low enough, means maybe your learning rate is not high enough, or maybe as well it means that your model, you're underfitting as well. Okay, that could be one of the two. Okay, you could be underfitting because you can't reach you cannot fit the model nicely. If you see oscillations like that, probably the learning rate locally at that, that range is too high as well. You can plot the accuracy as well, which is pretty much your loss function inverted. And to check overfitting, what you can check is look at the accuracy for both your training and testing set, or validation set, should I say. Okay, so you look both at the training set and what's going on in the validation set. If you're doing good, okay, so the training set, the accuracy goes, very high. But if you're unlikely that on the validation set you'll be doing as good, okay? So you probably will be slightly off. But if you're doing high overfitting, what you will see that your accuracy is going to start to deviate quite a lot from your training accuracy, okay? So if you start to you're doing okay, and then you're starting to go a lot worse with your validation, your accuracy, that means that you're totally overtraining your system, and then you're only doing good for the training, but anything outside of that will just be a failure, okay? So that's the point of the validation set, is to make sure that these two curves are somehow parallel and that you're doing good in both situations, okay? There's a lot of resources on the web. They're here. I advise you to look at those. We'll talk about the quick week 8 quiz later. I just wanted to finish by saying it's all fine. There's a lot of theory behind all that. But the reward is that this is Keras code, all the Keras code you have to train for MNIST, okay? This is all you need. This is how you define the network. This is like 5 lines of code. This is how you fit the model, do the training. This is another 5 lines of code. And you get 98.5% accuracy, okay? And most problems can be solved like this, okay? So all the theory you have seen actually ends up being something very succinct in just a few parameters in these Python models, okay? So kind of the hard part of the math is finished, and now it's all just playing with these things in a very concise way. All right, thank you.